So hey guys, welcome back to my YouTube channel. So in this video I'm going to explain the Prince algorithm, which is used to finding the minimum spanning tree, So first of all, let me explain the first of all we have to understood the concept of spine, that is minimum spanning tree. Okay, minimum spanning tree, minimum spanning tree. So so first of all we have to before moving to this main algorithm, that is Prince algorithm, let me explain this concept of minimum spanning tree. So what is first of all, what is spanning tree? So spanning tree means if we have n nodes. For example, if I have this graph that has n nodes, let's say this is node 0, which is connected to node 3. This is node 1, this is node 4, this is node 2. Okay, and these all nodes are connected to each other. So minimum spanning tree is we can say tree which has n minus 1 nodes, so this is the one, we can say this is the graph, undirected graph. So if I want to make the spanning, that is minimum spanning tree of this graph, then a definition of minimum spanning tree is we have n minus 1 nodes. Sorry, if we have n nodes, then we have n minus 1 edges, that is n minus 1 edges. If I have n nodes in my graph, that is in my original graph, then in this minimum spanning tree one's graph that has n minus 1 edges, and all the nodes are reachable to each other. Okay, all the we can say all the nodes should be reachable to each other. For example, if I make the spanning tree of this graph, then let's say let me give the weight of each edges. So weight of this from 0 to 1 is 2. Let's say this is 2, this is 3, this is 8, this is 5, this is 3, this is 2. Okay, so the minimum possible spanning tree will be, if I connect this, if I connect this from this, and this from this, and 2 from 1 from 2, and 4 from, so this is 5, this is 8, this is 2, this is 3. If previously if I sum up the edge weights of this graph, that will be 6, 8 plus 2, that is 10, 16, 16 and 5, 21, 21, 24, 26, that is 26. Now if I calculate the sum of all the weight edges, then it will be 10 and 18, that will be 18. So minimum spanning tree is we can say minimum spanning tree is simply, if I have n nodes, then in minimum spanning tree, then it should be we should have n minus 1 edges, and each nodes are reachable from each other. So, and there are many other possible we can say possible spanning tree of this graph. So the minimum, that and the all the among all the possible spanning tree, the minimum one that have edge weights less than others, or we can say minimum edge weights, that will be the our minimum spanning tree. Okay, so this will be the concept of minimum spanning tree. So if I have n nodes, so in minimum spanning tree, the condition there will be n minus 1 edge and each nodes will be reachable from each other. So and among all the possible spanning tree, the minimum the among all the, we can say, possible spanning tree, the minimum one that have minimum edge weights, sum of minimum edge weights, that will be our minimum spanning tree. So this is the concept behind this minimum spanning tree. Now let me explain this Prim's algorithm. So Prim's algorithm is used to find the minimum spanning tree. Okay, so now let's jump to the Prim's algorithm, that is Prim's algorithm. It is used to find the minimum spanning tree, that is MST. In short form, we can tell that it is MST. Okay, then so so let me explain this Prim's algorithm with the help of one example, we can say one graph. So let me draw the graph. So let me draw it. So this is, so this is my graph. Let me give the weights of each edges. So this will be node 0, this will be node 1, node 2, 3, 4, 5, 6, and edge weight will be 2, 4, that is 2, 1, 20, that is 5, 5, and 5. So this is my graph. So if I want to if I want to make the minimum spanning tree of this graph, that will be, so I have to choose the minimum edge weights, and in which manner, we can say I have to choose edge weights, or we can say edge weights in which manner we can say which have minimum weights. I have to choose the edges which have minimum weights. For example, in this case, if I want to connect the 0 to 3, then I have two paths. That first part will be from 0 to 1, and then 2, and then 3. Other will be directly from 0 to 3. That will cost me 20. That will cost me 20. Okay, and if I choose this longest part, that that will be cost me, that will be 15. So 15 is less than 20, so I will choose this longest path. So the my minimum spanning tree will be looks like, that is we will move from 0 to 1, which will cost 5, which have edge weight 5, and then from 1 to 2, I will move from 1 to 2 that have weight 5, 3, that have also weight 5, then 3 to 4, 4 to 5, and 5 to 6. And in that is in fourth node, there are also two, we can say, two paths from to connect two parts we can say two parts possible to connect to node 6. There are two parts for connecting to node 6. So first one will be directly, that will be, we can say, 4, and another is from 4 to 5, and then 5 to 6. So if I choose this path, that is 4 to 6, then this 5 will remain unvisited. Okay, so I have to choose, and then I have to this I have, if I want to visit this 5, then the total cost will be 4 plus 2, that is 6. So this will be we can say this will be costlier than this, that is 2. So I will choose this path, that is 2 and 2. This will be 1, 3 to 4 will be 1. So maximum that is at edge weight will be, that is 5 5 5, that is 15 16, and 16 plus 4, that is 20. Okay, 20. So this is the edge weight of minimum spanning tree. And if I calculate the minimum spanning tree of this graph, that is 25, that is 25 30 35 and 36 36 and 36 and 4 40 44 will be come 44 will be. So this is the minimum spanning tree, weight of the minimum spanning tree, so that will be 20. So the simple intuition is we have to choose the minimum edge from connecting from one node to another. And so simple intuition is we have to choose the minimum edge, so that we we can visit each node in we can say very low cost, or in minimum cost we can visit each node. So the intuition, we can say, so we have to choose the we can say minimum edge. So we will use for implementing this, we can say, implementing this Prim's algorithm, we use min heap, that is min heap. So min heap has the property of, that is the minimum element is at top. So let's say if mm, so I will take three variables. The first variable will be weight, that will be the edge weight, we can say. And another is, that is node to which uh, we have to go, node to which we have to go. Another is parent, from which we are coming from that node. Okay, to that node, this is parent node. So parent node will denoting the we can say the we can say parent of that node. And we can say we are coming from the origin, from which nodes previously. So this will denoting the previous node from which we are coming, and this node will be we can say from to which we have to go. Okay, so what I will do, I will simply take three values, that is first value will be weight, second will be node, and third will be parent. So let us dry run with this, we can say, this example. In this we can say, in this given example. So in first iteration, what will we do? We will start from any, we can start from any node. So we will starting from the zeroth node. So first of all, we will simply push 0 weight, because from 0 to 0 the edge weight will be 0, 0 to 0, and we have node 0, and we have parent, let's say, and we are taking the visited array. We are taking two arrays. The first array will be showing the visited, that will be size of the array will be number of nodes, that has 7 nodes. So 0 1 2 3 4 5 6. Okay, and initially we will mark all the we can say nodes unvisited, that is false. So all will be marked unvisited, and we will also maintain a, and we can say parent array, that will be denoting the parent of the each node from which we are coming, we can say to that node. So that will be this is parent array, that will be denoting the parent of the that node, particular node. Okay, and this will be the we can say visited array, that will be denoting the uh, number of nodes that we have visited or not. So this will be denoting the number of visited nodes. So initially the parent of we can say parent of all nodes will be -1. Then we will gradually we will we can say we will update the parent according to the our requirements. So later we will update the this parent vector. So initially it has -1. So initially the that zeros node have parent -1, because we are coming from that 0 also to, so this will be the -1. So this will be inserted into my that is main heap, that will be 0 0 and -1. Okay, now in our visited array the 0 will be marked visited. So I will write the true here, because this node 0 will be visited. Now I will pop this from my that is pop this 0 comma 0 comma -1 from my min heap. It is min heap. We are taking min heap because we have to we need the minimum edge. So min heap has a property that minimum element will be at top. So we are taking the minimum heap, and we are taking the visited array, which will indicating, or we can say which will denoting the our nodes are visited or not, or we can say keep track the or we can say which will keep track of our nodes we are visiting or not, or we have visited or not. And another vector that is parent vector, that will be keep track of the parent of that particular node to which we are going. Okay, so now now I will explore the we can say neighbors of 0, that is neighbors of 0. So 0 has neighbors, that is from 0 we can go from to 3 and 1. So my min heap will be look like this, that is both will be inserted into my min heap. Let me draw this min heap properly. So my min heap, let's say this is my min heap. Okay, this is my min heap, and then from 0 I can go to node 3 and node 1. So both these pairs are pushed into my this min heap. So the minimum the edge that has minimum weight will be come at top. So one from 0 to 1 the edge weight will be 5. Then node will be, we have to go to node 1. Then the parent will be 0, as we are coming from the 0, the parent will be 0. And here that will be, we have from 0 to 3 the cost will be 20. So 20, that is edge weight. And we are going from 0 to 3 and 0, the parent will be 0. Okay, so now what I will do, I will pop that the top element from my this min heap. So and I will also we can say I will also maintain a some variable that will be storing our sum of weights. Initially that is that is equal to 0. Then after the visiting this first, that is first node, then I have to add this 5 into my sum variable, that will be indicating the sum of all the edge weights of that minimum spanning tree. So now I have to mark visit to node 1, so I will mark as true. Okay, now what I will do, when I pop this 5 comma 1 comma 1 comma 0, then I will explore the neighbors of 1. So from 1 we can go to 0 and to 2. So 0 is already visited, so we cannot go back, so we will move to the node 2. So we will simply push the weights of, that is 5, push these pairs, and we have to go node 2 and we have parent 1. So now what I will do, I will mark visit, I will pop this top element and I will mark this 2 visited, and I will maintain this parent, that is 1 has parent 0 and this 2 node have parent 1. So I will add this 5 to my sum variable, so that will be 15, sorry, that will be 5 plus 5, that is 10. Okay, so I will pop this pair from the we can say from this pair from the my min heap. So now I will explore that this 2 neighbors of 2. So from 2 we can go to node 3 and node 1, and node 1 has already visited, so we cannot go back into my we cannot traverse back to node 1. So we will remove this and we will simply go to node 3 that has edge weight 5, and we have to go to node 3 and that has parent 2. So that has parent 2. So and then I will add this 5 into my that sum variable, that will be 15 will become. So after visiting 2 I will pop this pair from this min heap, that is 5, and I will explore the neighbors of the this 3 now. So from 3 we can go to node 0 and node 1. So not not 4, node 4. So node 0 is already visited, so we can we have to neglect this. So now now I have to move to node 4 that has edge weight 1, and we have to go to node 4 and the parent is 3. So I will mark visited to node 3, that will be true, and node 4 also, and the parent will be 3 and 4. 4 has 3 has parent 2, 1 has a parent 0, 2 has parent 1, 3 has parent 2, and 4 has parent 3. Okay. Okay, then after visiting the 4, I will mark the parent of 4 that will be 3. Okay, and I will pop that this pair from my mini heap and add the edge weight of 4, that will be 16. Total weight will be 16. Total weight will be 16. Okay, after that, when I come to this node 4, so I have 2, that is I can visit node I have two options. I can visit node 5 and I can visit node 6. So I will push this pair into my this mini heap. So that is the minimum edge weight will be come at top, that is 2, that we have to go 5, and parent will be 4. Another is that is has edge weight 4, and we have 6 and 4. So now I will pop the top element of my min heap and I will mark visited to node 5, and that will be parent of that will be 4. Okay, then I will add this 2 to my sum total sum, that will be 16 plus 2, that will be 20, that will be 18. So I will pop this pair from my mini heap and the sum will be, now my sum become 18. So now I have 5, so I will explore the neighbors of 5, that will be neighbor from 4 5 we can go to node 4 and we can go to node 6. So node 4 will be already visited, it is already visited, so we have to neglect this. Okay, because the we have condition in minimum spanning tree that we have to visit each node at once. Okay, and from 5 to 6 we are going with the edge weight 2, and we have to go 6 and from 5. So I will update the parent of this 5, that is 6 to 5, and this will be marked visited. Okay, so I will pop this pair from my that is from my mini heap. So this will be popped. So now the top will be this 6 4 6 4 4. So from 4 from 4 from 4 I can go to node 6 and node 5. So node 6 and 5 we can check, first of all we have to check the 4 is visited or not. So 4 is already visited, so we have to pop that this pair from the, we can say, this min heap, and after that we, the only one pair will be remaining, that will be 23 0. So we will see, we will check the condition. If my 3 is visited, I will check into my this visited visited array, is 3 is already visited. Yeah, 3 is already visited, so I have to pop this pair from my min heap. So now my min heap become empty, so I have get the minimum answer. So that will be 20, that will be 18 plus 2, so we have to add this 5 weight of into 5 in between 5 and 6, that is 2, that will be 20. So the minimum edge weight will be 20. So this will be the we can say simple algorithm of the Prim's algorithm, or we can say simple intuition behind the Prim's algorithm. So simply what we have done in this Prim's algorithm is simply we are choosing the we are choosing the edges which have minimum weights, and we have maintained a visited array which will we can say which will mark which will keep track of all the unvisited nodes, and once we have visited we will not go back into that node. So so let's go to the code part directly. So we have to simply write this code. So code is very easy. So if you have understood this, so code will be very easy. So first of all we have to declare the min heap. So first of all we have to declare the min heap. So first step is declaring the min heap. Min heap will be declared, that is priority queue, that will be priority queue, that is PIR priority queue. That has pair because we are taking the weight comma node, so we are taking the pair into comma int. The first one will be storing the, we can say, storing the edge weight, and another is storing the to which node we are moving. So next we have vector that has also pair, that is into comma int. That has into comma int. Vector p and greater that has pair, that is pq. This is our declaration of mini heap. This is step 1, that is declaration of min heap. Another step is, first of all we have to push the that is zeroth node, that is we are pushing this pair that is have zero weight, and from 0 to 0 we have to move 0. So 0 comma 0 we have to push, and I have to declare one visited array that will be keep track of our unvisited node, that is visited array. That size of that will be equal to the given vertices. So after that I will take one sum variable that will be indicating our edge sum of all edges, and I will simply run a while loop until our queue become empty, that is pq become empty, that is our min heap become empty, that is so first step is auto it, that is it dot first will give the edge weight. We will take the top element of this top element of the minimum spanning tree, that is pq dot top, and we will pop that top element. Okay, so my node will be at second place, that is it dot second, and my weight will be at it dot first. Now I will explore the, we can say, visited neighbors of that particular node. If this node is visited already, if this has visited already, so we have to continue, skip that node. Quanti skipped already visited. This will indicating the already visited. Okay, after that, if this node is not visited, then I have to mark this node as visited. Then I have to simply add into my sum that has edge weight. So sum plus equal to weight, and then I have to explore the neighbors of that particular node. ADJ, that is adjacent of that node, and simply I have to write adjacent node, that will be it dot 0, and edge weight will be it dot first. If our node, we can say adjacent node, is not visited, ADJ of node, then I have to push that pair into my mini heap. Push that pop pq dot push, that is edge weight, comma, adjacent node, and at the end we have to return the sum. At the end we have to return the sum. So let's see. To invalid argument, a priority queue, and that will be int comma int. So let me define the priority queue here, that is type dev, that is pair, and we can say int comma int, that will be p. Now in place of pair I can write p, only p comma, that is so let's see. I hope this should be work. I hope this should work. Okay, p is not declared in the scope. Oh, okay, we have to declare it at the top, that is here. I think. Type does not means, okay, I have to write the pair, this pair. So simply, so let's p think syntax error is coming in the this mini. Let me do the chat GPT for this. So chat GPT, where is chat GPT? So mm, correct this code. Okay, priority queue.